Hello viewers and welcome to another episode of Space Science with Python. In our session today we will continue working with the shape model of Churyumov-Gerasimenko. So last time we just used some Qt visualization method to show and interact with the comet model. And today I would like to put some more information into this model. So maybe using SPICE or some SPICE information to enrich our model with some more insights. And I was thinking, well, what could I add here? And the solution was quite obvious. I was thinking, well, let's use the landing of Philae itself. So you see here an image of the descent phase, during the descent phase of Philae approaching the comet. So this is what Philae saw during the descent. It initially should have landed somewhere in this region, if I recall it correctly. But unfortunately, Philae was not able to land there or to hold there. It rebounced and then it had a rebounce on the surface for a few times until eventually it landed in some cavity. And in this cavity, the solar cells were not illuminated by the sunlight. And then after some hours, eventually the battery died and the landing mission was completed. Now, the landing spot itself was later found by Rosetta. So you see here the surface of the comet. And here in this small region, it looks a little bit like a toy, right? In this large boulder field. There was Philae. Here are the legs, the deployed legs. And here is the upper body of Philae with some instruments. I think this is here part of the drill tower. And well, I was really lucky back in the days because I was part of the dust impact monitor team. So I was working on this instrument. I was there in the lander center during the descent phase and so on. So I don't want to make a storytelling YouTube video now. It was a very emotional and very inspirational day. And it was really a privilege to work on this. And now I can share a little bit my enthusiasm, my knowledge with you to show you how to compute Philae's journey on the comet. And for Philae's journey on the comet, we need several SPICE kernels. So we need, first of all, the shape model. That's what we have from last time. We need some time kernels and so on. You may remember this LSK kernel, but we need also the trajectory kernel of Philae on the comet. And this can be found on the ESA Rosetta repository. The link will be provided into the description. And the repository is huge, so there's a lot of different kernels in there and described in this aa-readme.txt. And this is the official repository with all the kernels. So predicted kernels, reconstructed kernels with different precisions, and so on and so forth. And unfortunately, there's no one single kernel for the descent phase and the rebounds phase. They are somehow separated. And I just downloaded for today's session the rebounds kernel, and it was here, this lorbcgfix rbd, which stands for rebound, and then I think it's the second version or so. So for today's session, all the kernels are in the GitHub repository. So if you make a most recent pull from the repository, you will get also the kernel here. But we will not plot the descent phase. Maybe this is a task for you with the knowledge you already have, with the things you already learned in my tutorial videos. There's only one thing that's quite important to understand, and it's the reference frame of Churyumov-Gerasimenko. So let's go maybe in our in our script from last time, but today, I will not. Oh, this is the wrong folder. I provided a new. I already prepared some Python script, some notebook, and there's some. I reconstructed or copied some parts from last time. So here, reading in some libraries, downloading the shape models. So the shape models need to be downloaded because they're too huge for the GitHub repository. Afterwards, we read in the comet shape model and do some very small data engineering. It's not really engineering, it's just shifting some numbers and then plotting the shape model in this Qt application or in VisVis. Now, Now the point is that when we compute the rebounds of Philae, we have to choose some reference frame. And fortunately, the reference frame we will use, it's called Churyumov-Gerasimenko fixed, so it's a fixed coordinate system. And the coordinate system, it's like, I mean, in SPICE you can define any coordinate system you want. You may remember we worked with the ecliptic J2000 coordinate system, J2000. I talked about the horizontal or azimuthal coordinate system, and there's also galactic coordinate system whatsoever. But with SPICE, you can also define your own reference frames, and that's what the ESA engineers did. They created their own Churyumov-Gerasimenko reference frame. And fortunately, the shape model is already provided in this reference frame. So all the vertices, they are already computed correctly. So all the pointing of all the vertices is given in this CG fixed coordinate system. Which means that for the descent phase, we can simply compute the descent of Philae, or not the descent, the rebounds of Philae, and simply plot it into our shape model, and then we are done. So we are quite lucky with this one. So let's maybe run the script from last time here, or some copies, some copied part of last time. See, I also removed the auxiliary function with this resolution because, yeah, my computer is not very fast with the high resolution model. Now I'm plotting the low resolution model. So you see here the comet. Let's increase a little bit the size of the window. And you see here the larger sphere of Churyumov, and here the smaller one. And if we align it like this, we see that we can reconstruct what Philae saw during the descent. So something like this. And the landing was somewhere here in the left part of this crater. Okay, so let's compute the trajectory of Philae and let's see what we can do. So I already, as I said, downloaded all the important kernels, so I will just load them in. We will talk about it in a moment. Shouldn't talk and type. Maybe like this. Kernels, first of all, the time kernel, the LSK kernel. I forgot the spicy pie. So Fernch, and then we have also the SPK kernel. This is also something I downloaded. And SPICE needs to understand the reference frame because it's not part of the standard repository. So it's not like ecliptic J2000, it's this fixed coordinate system. So some XYZ coordinates have been put into the center of the comet, whatever the center is, and yeah, then it was aligned somehow. And for this, we have a new directory, FK, for frame kernels, and there we have this Rosetta Churyumov-Gerasimenko reference frame kernel. So yeah, we will also learn in the future how to create our own reference frames, I don't want to reconstruct how I search for this and so on. Feel free to go into the repositories and read the documentation. It would be a little bit tiring for this tutorial video. Now let's take a look at the rebound kernel, because sometimes when I do something here, showing the time ranges and so on, it appears a little bit like magic. So let's obtain some information from this Philae landing kernel. So we use a new SPICE function, spk-cov, to read in this kernel, and then we need to provide an ID code for this for the object of interest. In our case is Philae. So Rosetta's NIF ID code is 226, and for Philae it's 226800. Okay, this is now something I know, but you could also reconstruct this here. But today we will just see, I want to see what is the time coverage of the kernel. So as I said, it's only for the rebound phases, and we would like to know what is the time range this SPK kernel is covering. So first we load the rebound kernel. It's not a string or whatsoever. It is something called spice cell. So it's a type defined by spice itself. So here the spice cell, and now you can obtain some meta information or so with this kernel. So first we need to determine the so-called cardinality. I will not explain it into detail, just using some function, but the cardinality of this one is very simple, as I think only 1, so it's not a very huge or complex kernel. So you see here's simply the number 1. Some kernels have larger numbers, so you have to be aware of this and then iterate through the kernel. Anyway, I don't want to bore you too much. What's interesting is that we can now determine the start ephemeris time and the kernel end ephemeris time using the function wn fetd. Now, this function sounds totally random, and yeah, in a way you're right. It's just about, you know, reading the documentation, working with it for years, then yeah, it's something that comes out of your mind. So we need to provide the rebound kernel and the cardinality. Now the point is it starts with 0, not with 1, so we have to subtract the number 1, but that's fine, I guess. We can then now print the ephemeris time, but well, the ephemeris time is just some time given in seconds. So let's use the function et to the date time, kernel start ephemeris time, and then provide it in some nice string format like years, month, day, hour, minutes, and seconds. So let's copy paste it and use the end. So we see now we will print in a human readable format the starting point and end point of the kernel that contains the information of the rebound phases of, or rebounds phases of Philae. So you see 12th of November, time range is around 2 hours, between 1530 and 1730. So that's basically the time range. And so what do we want to do? We want to compute the position of Philae, so the vector, and we want to have a NumPy array or list where every row contains the position of Philae at a particular time. And for this, we will compute the time between 1530 and 730 in, for example, 10-second steps. So we do this in a for loop. We say, okay, ephemeris time step in NumPy arrange, starting at kernel start ephemeris time and kernel end ephemeris time in 10-second steps. So per minute it's like 6 computations and 6 values, and then for per hour 360. So in total around 720. It's fine. So it shouldn't exceed our computational performance. Oh, I pressed enter, didn't mean to do this. So we can say Philae position vector append, and yeah, what spice function do we need to compute a position of an object? We use spk GPS, so it's not the state vector. So with the velocity, it's only the position vector. We provide the target. The target is Philae, as seen from the comet Churyumov-Gerasimenko. We will use the ephemeris time that is part of the for loop. The reference frame is this fixed reference frame 67p c minus g underscore ck. And I missed a comma. And the observer is the comet itself. It's Churyumov-Gerasimenko, which is 1, 0, 0, 0, 0, 12. And if you recall the function spk GPS or spk geo, it returns 2 values. The first is the vector, yeah, the position vector, and the second output is the light time. And we don't need the light time, we only need the position vector. So 0, the first entry. Oh, where's my cursor? There it is. And now we can convert the Philae position vector to a NumPy array. Yep, that's basically it. So let's have a look at this position vector. Now you see here the x, y, and z coordinates as of Philae as seen from the comet center in this reference, in this fixed reference frame. So this is what we need now to plot our lander's trajectory. For VisVis, or VisVis requires a certain format for this kind of information. I think I imported already VisVis, but yeah, what I want to show is we need. I'm confusing myself. From VisVis import point or point set. So point is for a single point, and point set is for what we have. So we say point set is Philae position vector. Yeah, so this is what we need from the documentation. Now here some parts reconstructed from last time. So now we just add our trajectory with VisVis plot, the point set. Then we say, okay, the line style should be a solid line. Line color, let's start with white, for example, and the line width is maybe 5. So that's basically it. So let's run this thing and see what happens. Ah, there it is. And you already see some white line there. You can do it also with the high resolution part of the comet. So there is our trajectory of Philae. So you don't know where Philae was initially landing. So the landing spot was here. So it landed here and then it jumped there. So it was flying around. Again, a touchdown, some other touchdowns, and then it landed here in this cavity. So you can move around a little bit with shift. We can also shift the comet itself. So let's have a look at the landing spot. So you see how Philae was jumping around on the comet. Yeah, this is really nice. So yeah, this is like, wow, now it's getting difficult. So this is how Philae was flying around over the comet surface. So yeah, unfortunately, it didn't land on the initial spot. It was landing in this cavity, but yeah, it's pretty impressive what kind of jumps this small object did. Pretty cool. So yeah, this is what I wanted to show you, how we can add more information. You can also, maybe you can, yeah, as a small task maybe for you, you can now plot also the descent phase of Philae. So use the other kernel, search for it to show also the descent phase. And another thing you could also do is during the descent phase and rebound phase, compute the direction of the sun and change the position of the sun accordingly. So you can create a small animation or so. And here in this part, the light position, I just put up a random number. You can replace it with the direction to the sun. So this could work. And then you see also some more realistic illumination patterns as it was seen, or as it was during the descent phase. Yep, so this is the story of Philae and its rebounds, or yeah, rebounds journey over the comet surface. Was around 8 years ago now. Yeah, so Philae is probably already covered in some dust or so. Rosetta was also landing at some point on the comet, end of the mission. And we are here on Earth with all our data to reconstruct this amazing journey and scientific and engineering. I don't want to say miracle, but yeah, masterpiece, let's say. Okay, so this was what I wanted to show you in today's session. I hope you liked it. I hope you enjoyed it a little bit. And again, the code is on GitHub, on the GitHub repository. Feel free to play around, change some values, try to determine maybe also the distance between the comet and the and Philae. You can compute also the kinetic energy, for example, and see how much energy the lander lost with every impact, or where the impacts were, the rebounds. And that's everything for today. So until next time, take care and goodbye.